Hello, we're doing acceleration questions and problems. This is set number 1, and we're going to do problem number 2. So the second calculation. They say a car accelerates from 12 meters per second to 25 meters per second in 6 seconds. What was its acceleration? And how far did it travel in this time? And we're going to assume the acceleration is a constant value. That's important. The equations that we're working with, they all have this requirement that the acceleration be constant. If the acceleration is not constant, then the formulas don't really apply, and you'll have to use somewhat more advanced methods to do your calculations. In fact, you'll likely be using calculus to solve. But here we go. So I'm going to go ahead and draw in a little sketch first. Why? Is it because you just like drawing pictures, Mr. C? Well, maybe. Maybe. So let's see. Now you're wondering, what kind of car can I draw? I don't know. I like drawing convertibles. Okay, good enough. Good enough. Far too much detail. Okay. Yeah, you know. Yeah. There we go. Okay. Just kind of hanging out, driving his car. Okay. Anyway, now it's going to accelerate from 12 meters per second, and then faster, faster, faster. And down the road, he'll eventually be going at 25 meters per second. Okay. And the time to do this, the time to get there, is going to be 6 seconds. Okay. We want to know what's the acceleration. And how far did it travel? How far? That is the question that we can answer 2 ways, with distance or with displacement. In this case, we're going all in one direction, positive direction the whole time. And so our speeds will always be positive, but our velocities will also be positive. We'll get the same answer out, whether we're doing speed or velocity for this one, or distance or displacement. So by how far, we're going to call this displacement. Why not? Okay. So this is what we've got. Hey, what's this 12 meters per second? That's a velocity, meters per second. That's my starting velocity. And the 25, that's my final or ending velocity. So that's what I've got to work with. And so you say, all right, cool. I can see what I've got. You say, which one would you like to solve for first? Well, acceleration tends to pop up in a lot of the formulas. So let's find that acceleration first. So I don't know the delta x. I don't want to have 2 unknowns in the equation. So I'm probably going to want to use an equation that doesn't have delta x. And when you look at the formulas, this is the accelerated motion formula that works. V is at plus v naught. All right. And we are trying to solve for acceleration. So I might rearrange this, subtract the v naught over, divide by t. I'm going to get that a is v minus v naught over t, or delta v over t. Substitute in my values. My final velocity would be 25 meters per second minus my original velocity of 12 meters per second divided by the time, 6 seconds. I have known physics teachers who are really picky, and they want you to put your units on like every number in the calculation. So like meters per second, seconds. I am good with just checking and making sure that my units all match up. All my times are in the same unit, all my distances are the same unit. And then I'm pretty confident. Velocity is in meters per second divided by seconds. I know I'm going to get an answer in meters per second squared out here. 25 minus 12, you see that would be 13. 13 over 6. This is where I reach for my calculator. And I get that that is 2.1. We'll round to 6, the third digit there. So this would be 2.17 meters per second squared is my acceleration. Now they ask, hey, how far did it travel? So we're trying to find the displacement here, the delta x. And you say, well, you know what? We actually have kind of our choice of a couple different formulas here. You say, there are 2 formulas here that have delta x in them for accelerated motion. One of them says displacement is v naught t plus 1/2 at squared. Oftentimes this delta x gets split apart into final minus initial. And so when you do that and you substitute in a final minus initial, right? And then you add the x naught, the initial position, to the other side, it'll look like this. I think this is the way that your textbook shows it. And that's fine. It's the same thing. What this points out is that if I think about, once I do something like this, though, I have to decide when I drop my coordinate axis where I'm calling position 0. Most of the time, we'll just pick the starting position here, where he's going at 12 meters per second, and we'll say, hey, where the car is at that time, we'll say that that's position 0. Well, if he starts at 0, then this term just drops out, right? And my final position is the same thing as my displacement. So if I start at 0 and I end at, well, we're going to calculate it out in a minute. Just say we ended at 200 meters, say. Then the displacement is 200 and the final position is 200 because the initial was 0. It's just going to drop out. So it just kind of turns into be equivalent to that anyway, if we're starting from 0. But anyway, moving onward. So we're trying to find this displacement. We know v naught t plus 1 f at squared. If I continue on here, I can call this starting position 0. Starting velocity, we know it was 12 meters per second. The time that this took, we were told, was 6 seconds. Plus 1/2 my acceleration. We just solve for up here. 2.17 meters per second squared. And then the time again was 6 seconds. And so I can do the math here. 12 times 6 plus 0.5 times 2.17 times 36. And when I do that, I get a displacement or final position, because initial was 0. I'm going to go ahead and see that the distance it went was in fact 111.06 is what I got. But the thing is, see that 2.17? That value actually I rounded off to get. All right. So my precision isn't that great. Are we really going to worry about it? In my calculator, it's 111.06. I'm just going to round that up to 111.1 and feel just a teeny bit guilty that I wasn't careful about significant digits, but not that guilty. So we're around 111 meters for our displacement. Couple things you'll notice, of course, that as I do my work, oftentimes I have a sketch. I'll have the formulas I'm using, and then I show the formula, and then I show the values substituted in. And I work vertically. This helps keep my work organized and makes it easy to follow. When you go vertically, you can see, oh, this V, that was the 25. This V naught, that was the -12. This T, that was the 6. You can see how things get subbed in, and it's really easy to follow along the work. And it helps you think through the problem as you're going. So strongly recommend that. All right. And that's, I think, what I have to say about this problem.